This is a flip video about conjugate pairs. In order to discuss conjugate pairs, let's first remember some of the things we learned in our last video. So if you remember, we talked about acids and bases, defining them as Bronsted-Lowry acids and Bronsted-Lowry bases. So let's revisit that definition. A Bronsted-Lowry acid is one that donates an H+. And remember, we can call an H+ a proton. A Bronsted-Lowry base is one that accepts that H+, or that proton. So if you remember this reaction from the video, we have hydrochloric acid and we threw it in water. Remember, I can either write water over the arrow or plus H2O as a reactant. And we know that the acid dissociates into H+ and Cl-. But that's not the whole picture. So what really happens? Well, what really happens is seen here in the beaker. So if you notice, I throw my HCl into water. Same thing happens. H and Cl dissociate or ionize. I see them come apart. But what really happens that I didn't mention last time is that the water snatches up that hydrogen. It actually takes the hydrogen onto it and forms what's called a hydronium ion. See, the water is now has an extra H+ attached to it, and that's called a hydronium ion. The chloride ion is seen here floating around, right? Let's write it down. The hydronium ion has a little plus there because there is an extra hydrogen with a plus. H3, 1, 2, 3, O, plus. Okay? So really, the more proper way to write this is seen here. HCl thrown into water yields H3O plus Cl-. So really, this H+ and this H3O+ are the same thing. The H+ is kind of like the abbreviated version, but the H3O+ is what really happens. Okay? So with that being said, let's ask ourselves then, who is doing the donating and who is doing the accepting? So let's apply our Bronsted-Lowry definitions. Remember, the acid donates and the base accepts. So the acid is this one seen here because it donates its 1H+, let's draw an arrow, to the water. How do I know? Because H2O became H3O+, and I just saw it happen in the beaker. So the acid donates. Well, didn't we just say that the base accepts? Yes, that's right. Water is a base then in this instance. And that's true. Water can act like a base. And I know you're thinking, I thought water was neutral. Well, according to our Bronsted-Lowry definition, water is acting like a base. So a base accepts. Now, the reason why I know this to be true is because I always look at it like my reactants are the first part of the story. In order to figure out what my reactants are, I look at the final end of the story, which is seen here. And I say, what happened in the beaker? This side tells me what happened in the beaker. This says H2O became H3O+. So I now know the story of water. Water accepts the H because it turns into H3O+. I know the story of the acid because I look here and I say, oh, look what happened to the acid. It lost or donated its hydrogen. How do I know? Because on the other side, it's missing its hydrogen. Remember, when you pluck off an H+, you're left with a Cl-. Okay? These, over on this side, have names. So what you want to do is you want to find the pairs. HCl and Cl- are pairs. H2O and H3O+ are pairs. And we call these conjugate pairs. So they kind of look alike. Now, the acid and its pair is called the conjugate base. The base and its pair is called the conjugate acid. Now let's stop for a second. That's a little confusing, and let's talk about this. So the acid, because it lost its H, loses that acidicness. See, over here, it lost the H, so it turns into the base. We call it a conjugate base. The water, which was a base to begin with, because it accepts, right, it now turns a little bit more into an acid, so we call it the conjugate acid. This is the base, that's the conjugate acid. These are pairs, and these are pairs. So let's put conjugate acid and base pair as a definition, and let's see how we can define it. A conjugate acid-base pair differs by one proton. That's another really good, easy way to do this. So let's take a look back again. HCl is paired up with Cl minus. They differ by one proton. I have one H plus here, and I have 0 H plus. 0 minus 1 is 1 proton. That's a pair. Let's see if this is a pair. I have 2 H pluses here. Here's the 2. And I have 3 H pluses here. The difference between 3 and 2 is 1. All conjugate pairs differ by 1 proton. So let's take a look at some others. Okay, let's just take a look at some basic conjugates seen here. All right, so these are conjugate pairs. How do I know? HF and F minus. F minus lost its proton. 1 proton here, 1 H plus, 0 H pluses here. That's a differ by 1, so those are conjugate pairs. How about here? Are these conjugate pairs? I have 4 H pluses and 3 H's. H pluses here eventually, right, if this was to pull off. So 4 and 3 H's differ by 1. So you want to count the hydrogens to see. And then they pair up. Okay. Okay, seen here I have HBr and H2O. And then on the other side I have my products. So let's assess this and figure out which of these is the acid and which of these is the base. Well, I find HBr, and I find the substance that looks similar to it on the other side. Here it is, Br minus. Are these conjugates? Definitely. By definition, they have to differ by 1 hydrogen ion. I have 1 H here, 0 H's here. That's a difference of 1. So I found my conjugates. Now, what happened? HBr, at the end of this reaction, lost a hydrogen. In other words, it donated it. How did I know? It started off with 1 and then it no longer had it. If you start off with an H and then at the end of the reaction you don't have it, it means you donated it. So let's put that here. It donates. So who donates? Remember, Bronsted-Lowry's definition, acids donate. So that's the acid, right? That's how I figured this out. Remember, an acid is paired up with its conjugate, base. Acids pair up with conjugate bases. Now let's do the next one. Well, if this is the acid, this must be the base. How do I know? Don't forget to draw the arrow in. If HBr is donating, there's only one other thing in the beaker to donate to, and that's water. There's nothing else in the beaker here. Okay? So H2O is accepting. See how the arrow is pointing to water? It accepts an H+. According to Bronsted-Lowry, if you accept an H+, we don't need all that. If you accept an H+, you are a base. So let's label that here. It's a base. Okay? Let's find its conjugate. Well, it must be the other thing, right? Let's make sure that works out. First of all, they look alike. If you notice, conjugates look somewhat alike. Then the real definition is they differ by 1 hydrogen plus. So I've got 2 H's and 3. There you go. That's a difference of 1. These are conjugates. We label this base, and on the other side is its conjugate acid. So on this side, we label these either as acids and bases, and those get labeled as the conjugates. So in summary, it might be good to kind of write this down, that acids are linked up with conjugate bases, and bases are linked up with their conjugate acids. Let's try one more for practice. Okay. Remember, this is what happens in the beginning, and this tells me what happens at the end. I find the things that look alike. I say this and this look alike. And I ask myself, are they pairs? If they differ by one H plus, they are. I have one H here, no H's here. That's a difference of one. This is a conjugate pair. Now I ask, what is happening? Well, I look on this side of the story and say this one started off with an H, and then at the end of the story, it lost the H. How do you lose an H? This donated its H. Who was the only thing in the beaker to donate to? The water. So a donator is the acid. Acids donate. Who accepts? Bases. So already I figured out my acid and my base. Now remember, an acid is linked with its conjugate base. Careful, it has to be a conjugate base. Well then, what's left? These two are left. So I'll link them up down here. It doesn't matter where you link them, as long as you link them. Do these differ by one proton? Yes. 2 H's and 3 H. 3 minus 2 is a difference of 1 proton. So we know that these are conjugate pairs. Remember, a base is paired with its conjugate acid. Okay? That's the end of the video. This might be a really good video to go back and review some of these examples.